Ok, vi skal bytte språk. Jeg skal ganske straks si velkommen til Ulf Schøneberg. Han har titlen Head of Data Science hos The Unbelievable Machine Company i Tyskland. Jeg elsker jo navnet på dette selskapet, det er helt fenomenalt. Dette er et søsterfirma i Base Farm-gruppen. Han har bakgrunn som matematiker og har jobbet blant annet som forsker og programvarearkitekt. Foredraget hans har titlen Why Should I Trust a Statistical Data Model? Welcome to the stage. Give him a round of applause, please.
My name is Ulf. I'm a mathematician, and I would like to talk about n-dimensional differentiable manifolds, right? This is the math talk, is it not? No. I'm the head of data science at the Unbelievable Machine Company. We get 10 this year, and we are a part of the Base Farm family. I lead a team of 15 data scientists. It's 50% girls, 50% boys. We almost have a PhD in some special area. We have physics, we have mathematics, we have computer science and linguistics. And I started like 3 years ago at Unbelievable Machine as a normal data scientist. And last year in November, I became the head of the team. And I would like to talk about a few use cases, but also about some theoretical things that are related to machine learning. I understand I'm the only lecturer today in English, and my Norwegian is like very minimal, but I had understand that künstliche Intelligenz is almost the same like in Germany, right? So that's nice. Why should I trust a statistical model? Like all these künstliche Intelligenz, artificial intelligence stuff that got so popular and every application has to have it, is basically statistics. It's statistics on steroids, but it's statistics. It's nothing fancy about artificial neural networks that sounds so nice, but there is no brain-like thing involved. It's a network, it's a complicated thing called a manifold, a mathematical manifold, but it's like a very complicated net in high dimensions. So, there are a few other statistical models out there that are very popular. Everybody is talking about neural networks, but decision trees are also, when it comes to certain kind of problems, very, very effective. We worked like UM as a company, and especially the data science department is, we don't have a product or something, we sell our knowledge. So the customer usually comes to us approaching and has a certain problem in mind, and we are to solve the problem. When it comes to, I thought about what to talk about when I was asked to speak here, and we discovered a couple of use cases related to the financial sector that usually has something to do with fraud detection, with prediction of user behavior. There's another whole area, it's called closing case prediction, and also the thing that you want to learn why your customers are leaving you. This area is called churn prediction. And I have a use case for every part of this. But maybe it's a good thing to bring a little bit of structure into the whole, AI is a wave. It's like it's a hype thing. And I'd like to talk about 3 waves of artificial intelligence. I borrowed this title from the DARPA. These guys really know what they're doing. So the first wave of AI is rule-based systems. We all use them. Almost everybody of you has a computer that he uses, and there are programs on there, and this is just a rule-based system. Somebody solves the problem for you from a very specific domain, and then he hard-coded it in a programming language. These programs are incredibly good. We all use them, but they are very bad when it comes to things with a vague character, like recognizing a face or recognizing a voice. There is no way to write that in code, at least not a good way. And this brings me to the second wave of AI, and this is statistical learning. This is the wave we are currently in, where all these, not all, but a few algorithms are becoming better and better. If you talk on your phone to Siri or to Alexa or to your Google Assistant, you have recognized that during the last days they got significantly better and better, and because of neural networks and because of manifolds, and I come to this later. Of course, the first wave of AI, it's not obsolete. It's just an addition to the second wave. So the first and the second wave, they go together. The first wave is still absolutely fine when you want to solve problems, and the second wave, it gets better. The third wave is the wave we really want as machine learners or as customers. The third wave would be nice to have. We don't have it yet, but we have a few expectations. So these second wave AI systems, they work very well. You train a neural network with data, like with a lot of data. You can start with a few hundred data points or a few thousands. You need millions of them. And when you train it, a very complicated a manifold exists in your computer or somewhere, or in your GPU. And that's basically a matrix with numbers in it, with millions of numbers. So when you try to figure out why your neural network has made a certain decision, you can look into these numbers, but how useful is it to look into millions of numbers? Ask yourself, that's impossible. And we don't have mathematical methods to do that. So these second wave systems, they work like black boxes. I have it here. So I call it black box AI. Everybody else calls it that way too. So these neural networks and all these modern algorithms out there, they almost work as black boxes. There is no way to look into them because they are so big. I had a customer, I personally had that customer, it was my third use case at I guess. It was a very big German travel agency. I think it's one of the biggest. And they asked us to predict the prices of their flights according to the prices of their opponents. Usually for years, they had people sitting in front of a computer doing that, and they had guts feeling how to do that, and they just adjusted the prices according to that. But okay, it's the 21st century now. They heard about machine learning and they asked us, can you do a model for us? And we said, yeah, let's see. Let's have the data. They had good data. Like, there is no such things, such good data out there, never. But they had relatively good data. And we trained a decision tree on that. It took like a few weeks to train it with data cleaning together. And then the algorithm became as good as the guys with the guts feeling. And there's no wonder to that, because we used the historical data that these guys produced to train the net. And we are not in an area like Google with AlphaGo, where we can start at that point and then play like, have a virtual opponent to play these poker games about prices that one algorithm gets better and better. It's not possible in that case. But okay, we managed to do that. And then it was the CEO, I guess. It's an old guy. It was an old guy. And he asked, okay, you did that. Can you explain it to me? And I said, no, it's impossible. The tree is 40,000 branches long, and they all involved in the final decision. So how can we explain it to you? It's impossible. And he said, if you can't explain it to me, I will not use it. What? But in the end, he didn't use it. It's a real story. I mean, maybe it's understandable. People tend to do that when it comes to money, right? And he's not so very, very far from. Actually, there are a couple of good examples out there where your model is very good in 99.5% of all the cases, and then in this 0.5%, there is this really catastrophic error where you can't say why is this doing that. And that brings me to manifolds. Hello, there's math here now. A manifold is a very complicated structure, but it's all about understanding how the computer learns, right? I mean, people tend to say the computer will just learn that. You hear this a lot. It's called machine learning, right? So, but is actually nothing could be further from the truth. There's a lot of there's a lot of effort that goes behind the scenes from people like me and my colleagues to create a system that a computer can learn. Data scientists take time to create statistical models that characterize the problem domain and then trains these models with very specific data and with large amounts of data, and then something comes out. Maybe it's helpful to touch just a little bit of higher mathematics at this point, just a tiny little bit. There's these things I told you now 3 times, I guess, the manifold hypothesis. And a manifold is a structure in geometry, in high-dimensional geometry, but let's stick to it's not 3 dimensions, it's more, but let's stick to 3 dimensions. A structure a manifold is a structure in geometry where data is grouped together to cluster and form substructures that lay in much larger embedding spaces, larger in terms of having more dimensions. And it turns out that when we are dealing with data from the real world, like looking at pictures or listening to sounds, the data it forms clusters, like abstract clusters. And we train an AI system to understand how to separate these clusters. These clusters can be like everywhere in a very complicated room, and they can be entangled and stuff like that. And what an AI does is it twitches the room, the data room. It stretches it. It does some twinching, scaling to these data points until these clumps separate. This is basically what it does. You can imagine that on a piece of paper, but you can also do it in 50 dimensions. It's all the same. So, neural networks sounds fancy, like artificial neural networks. They have nothing to do with neurons. There is some model from the 70s that describes a neuron in a mathematical way that has a little bit of similarity to what we are using, but there is actually no real connection. The brain is working totally different, like these artificial neural networks. They sound complicated, but what they really are, they are just spreadsheets on steroids. That's all there is to them. So, they are black boxes and they are bad and whatever. So, let's talk about Whitebox AI, and my time is running out. So, instead of having black box algorithms, we like to have the opposite, right? We like to have white box. White is not the opposite of black, but maybe transparent algorithms that can some facts about machine learning in general. We have this model, and this model is agnostic to the world. It just, you feed in data and you get out data. That's a very common saying between my colleagues and me. It's, to make it very short, it's garbage in, garbage out. You have this algorithm. If you feed in garbage data, you get garbage predictions. it's not that, and sometimes it's very hard to see why the garbage is garbage. So it would be nice to have a method that the algorithm is pointing out, there is something fishy about that prediction. Can you look it up? Can a human please have an idea? There's this famous use case of I think it's a Chinese manufacturer. He they had their laptops out, and they trained it on basic face parts, and they trained it on. They thought they trained it on almost every people. And the main part of a face recognition algorithm is looking at the eyes, because they are very significant, right? It turned out that they had forgot, and there's a certain group of people from Asia, when they tried to unlock their laptops, it was impossible to do because their eyes weren't recognized as eyes. They were just black boxes in there. So that's a famous example to do that. So it's an acronym. It's a very long word. Local interpretable model agnostic explanations. In short, it's LIME. LIME is an algorithm from the Python universe. I mean, machine learning is mostly happening with people's. They use tools, toolboxes, software toolboxes, and some toolbox got very famous and popular. It's scikit-learn, if anybody had heard of it before. But we usually, me and my colleague, we usually use Python as the main programming language. And then we use this scikit-learn library a lot to solve almost every problem. There are a lot of predictors out in there. There are equation solvers. There are like genetic programming stuff, neural networks. There's we have all this out there. It's in there. It's a piece of software from the Google Summer of Code from 2012, I guess, I don't remember. But this LIME library, you can add or you can add it to almost any method that it's in this toolbox. It's model agnostic, so it's even agnostic to models that are not still invented. There's a concept behind this LIME package. You can use it with every predictor, with every machine learning library, and you can say, okay, tell me why this decision, why the algorithm has made this decision. When you have a picture and you want to have a classifier with a cat and a dog, and it says cat, and you say, please explain that to me, it will give you back the picture with a highlighted cat. And when you do it with text classification is usually a domain from the NLP universe. It will highlight you the words. I mean, you have this simple, everybody is capable of understanding this ham-spam thing. So if the algorithm categorizes this message as spam, it will highlight you the words. That's the use case, or that this. The most use cases I discovered when I work with customers from the financial sector is they are very like this travel agency guy. They say, okay, if you can't explain it, I will not use it. Almost all the bank customers I worked with have, over the years, for fraud detection, for instance, they have developed this very sophisticated rule sets, like really long lists of rules. Okay, if this is happening, then the rating goes down. If this is happening, then the rating goes even down more. If this is happening, it goes up a little bit, stuff like that. So all these customers have these rule sets. The problem is, with rules, you can't work on the second wave of AI because it needs data points, like lots of data points. So we come up with the idea, and not only we, like a lot of people come up with the idea to have a data point generator, like a very sophisticated random number generator that generates data points that are, most of them are useless. But you feed them into this large list of rule sets, and all the garbage will automatically filtered out, because I think the rule sets are sophisticated enough to do that. and what's coming out of them is valid data points. And we can use these valid data points to train the statistical models that got so good at everything. That's it. Thank you.
Thank you. So, we have a question from the audience. I'll just pick up my phone and we'll see. Just a second. Here we are. Okay. So, it goes. What is the most complex problem you have solved using AI and machine learning?
The most complex problem was probably also the use case I love most about working at UM. We fed an autoencoder. It's a special kind of artificial neural network with the data with the sound data of bearings, the bearings of windmills. These windmills, these bearings in the windmills, when they get louder, they are about to fail. I mean, the probability is rising when they get louder, but they also get louder when the wind is blowing harder. So we trained that network to separate or to predict when the bearing is about to fail. This is, of course, the most complex one.
It's very concrete. Very nice. Thank you.
Thanks. Thank you.